Greetings and welcome back to Conic Sections in Pre-Calculus. Today, while Mia's apparently having a bit of a rest, we'll explore the world of parabolas in what's probably a new way for you. Before starting this lesson, review how to find the distance between a point and a line in the coordinate plane. If you haven't already, pause the video to complete the warm-up and the pre-video activity on the first 2 pages of your lesson notes. When you're done, resume the video. Now, let's explore parabolas. You know the parent function for parabolas as y equals x squared, which looks like this on the coordinate plane. You've learned to write quadratic functions in standard form, vertex form, and factored or intercept form. You've also learned how to transform parabolas by translating, stretching, compressing, and reflecting them. Just as circles are defined as the set of all points that are equidistant from the circle's center, parabolas also have a formal definition. Let's begin here. We have a point and a horizontal line on the coordinate plane. In the context of parabolas, the point is called the focus, and the line is the directrix. A parabola is the set of all points in the coordinate plane that are equidistant from the focus and the directrix. Think about what this definition means as you fill in the vocabulary blanks in your guided notes. What does this definition tell us? Consider the term equidistant. If a point is halfway between the focus and directrix, is it equidistant from both? This might sound obvious, but it helps us understand the definition. How far is this point from the focus? 1 unit. How far is it from the directrix? Remember, when measuring the distance from a point to a line, we measure perpendicularly to the line. So we wouldn't measure these slanted distances. Since the directrix is horizontal, we measure straight down vertically, perpendicular to it. What is this distance? Yes, it's also 1 unit. The point halfway between them is equidistant from both. Now that we have one point equidistant from both the focus and the directrix, let's find more. How far apart are the focus and directrix? Yes, they are 2 units apart. How does that help us plot more points? Knowing the focus and directrix are 2 units apart, we can say any point on this parallel line is also 2 units from the directrix. How do we use this to find more points on our parabola? Points on the line that are also 2 units from the focus satisfy the parabola's definition. So, let's measure 2 units horizontally from the focus to the right. This point is 2 units from both the focus and the directrix, so it's also on our parabola. I always think of an imaginary square when measuring like this. Look at the left side of the y-axis. Can you see where the square would go? If we imagine a square with one vertex on the focus and one side on the directrix, we can find another point on the parabola. Where would that be? Right! Placing a point at the upper left corner of this square, we know it's equidistant from both the focus and directrix. We're going to see this square again, so take note of the fact that its side length is equal to the distance between the focus and the directrix. Now we have 3 points on our parabola. The first one we plotted is the vertex. Connecting all 3 points with a smooth curve reveals our parabola. Every point on this parabola is equidistant from the focus and the directrix. To help you visualize the idea of equidistant more clearly, let's expand on the definition of a parabola. Even though we used just 3 points to graph it, there are infinitely many points on a parabola. For example, consider this point on the parabola. If I told you its distance to the focus was 2.8 units, what would you say about its distance to the directrix? Exactly! It would also be 2.8 units. Now, what about this point at negative 2.83, 2? How far is it from the focus? If you said 3 units, you're correct. Do you see why? It's 3 units from the directrix, so it must be 3 units from the focus as well. Now that you've seen how the formal definition of a parabola helps us plot it on the coordinate plane, let's use the focus and directrix to derive the parabola's equation. Here we have a parabola with its focus and directrix shown, along with a point on the parabola that represents any point except the vertex. We'll label this point as x, y. The distance between the vertex and the focus is a directed distance, which we'll call p. Usually, distances are positive, but with directed distances, the sign indicates direction. If p is positive, move in the positive direction. If p is negative, move in the negative direction. Here, our parabola's vertex is at 0, 0, and the distance to the focus is p. So the focus is at the point 0, p. The distance from the vertex to the directrix is the opposite of p, making the directrix equation y equals negative p. Now let's turn our attention to the point xy on the parabola. The definition of a parabola tells us this point is equidistant from both the focus and the directrix. To verify this, we need the coordinates of the point directly below, xy. What are its coordinates? This point shares the same x-coordinate as xy since it's vertical to it, and being on the line y equals negative p, its y-coordinate is negative p, so this point is x, negative p. We can define d sub 1, the distance between the focus and the point xy, by using the distance formula. d1 equals the square root of x minus 0 squared plus y minus p squared. Next, we'll measure d sub 2, the distance between xy and the directrix. Just like you did in today's warm-up, we measure perpendicularly to the line y equals negative p to get d2 equals the square root of x minus x squared plus y minus negative p squared. And what do we know about d1 and d2? Right! By definition, they are equal. Let's set these two expressions equal to each other and then simplify. We know d1 equals d2, so let's substitute the expressions we found using the distance formula. I see some simplifications we can make, like x minus 0 and x minus x. Next, let's square both sides to make the equation easier to work with. Then, we'll expand both perfect square binomials. Next, cancel the like terms. After simplifying, we get this expression. What's the final step? Right, combine the py terms and rewrite it as x squared equals 4py. The equation we've derived after setting d1 equal to d2 is the standard form of a vertical parabola with its vertex at the origin. And what is p in this equation? Remember, we defined it earlier. P is the directed distance between the vertex and the focus. Now that we've derived the standard form of a parabola, let's go through an example to create a graph from the standard form equation. Here's an equation in that standard form that we just found. X squared equals 12y. Let's graph it together. In this form, we know that the vertex is at 0, 0. To graph any parabola, we need the vertex and at least 2 other points. To find those 2 points, we'll need the focus and the value of p. Remember, p is the directed distance between the vertex and the focus, and we can identify p from the standard form. X squared equals 4py. Here, 4p equals 12, so we know p is positive 3. That means the focus is 3 units from the vertex in the positive direction, so the focus is at 0, 3. The directrix is 3 units in the opposite direction with the equation y equals negative p, or y equals negative 3. So let's sketch that in too. Okay, what's next? To help us plot additional points on the parabola, I like to imagine that square we discussed earlier. Remember, this square's side length is the distance between the focus and directrix. How far is that in this case? Right, 6 units. Can you think of a way to determine that distance from what we've already done? The distance between the focus and directrix, as well as the side length of our square, is 2p. By placing a square with a side length of 2p, or in this case, 6 by 6, so that one vertex is on the focus and the opposite side is along the directrix, the square's opposite vertex gives us another point on our parabola. This point is 6 units from both the focus and directrix. Okay, we have 2 points. Time to plot a third. Can you think of a way to do that without drawing the square? Let's do some mental math and count out 2p units horizontally from the focus, but this time in the opposite direction. 6 units to the right of the focus is the point 6, 3. Now that we have the vertex and 2 other points, we can connect all 3 with a smooth curve to reveal our parabola. X squared equals 12y. Okay, here's something interesting. What if I gave you a graph with a focus at 1, 0 and a vertical directrix at x equals negative 1 and asked you to draw the associated parabola? What would you do? Using your guided notes, try to find and plot at least 3 points that are equidistant from the focus and directrix shown here. The parabolas you've seen in the past have all been vertically oriented parabolas, opening up or down, and have passed the vertical line test as functions. But remember that we're learning about conic sections. The cones we take slices out of can go in any direction, including horizontally or at an angle. Even with a vertical directrix, we can find all points equidistant from the focus and directrix. To plot 3 more points that are equidistant from this focus and directrix, should we find p first or find the vertex first? It's actually a simultaneous problem. P is half the distance between the focus and the directrix, and the vertex is at the midpoint of the perpendicular segment connecting them. We can see that the vertex is at 0, 0, and P is 1. If P is 1, 2P is 2. We can use an imaginary 2 by 2 square to plot additional points. Or we can simply count up 2 units and down 2 units. Connect everything with a smooth curve to reveal a horizontally oriented parabola. Now that you've seen a horizontally oriented parabola, let's figure out what the equations for horizontal parabolas look like. How might the equation for a horizontal parabola differ from or be similar to that of a vertical parabola? Make a prediction, then find the section in your guided notes titled Horizontally Oriented Parabolas to derive the equation, just like we did for the vertical one. Here's a hint. Start with the distance formula. Great work! You should have used the distance formula and simplified, similar to earlier, and found the equation y squared equals 4px. If you got stuck, pause here to review the steps in detail. You now have the formal definition for both vertically and horizontally oriented parabolas, and you know their standard form equations when the vertex is at the origin. How can we remember which is which? For vertically oriented parabolas, the x variable is squared, just like you've seen before. For horizontally oriented parabolas, the y value is squared. But what if we move these parabolas to different locations on the coordinate plane? How would their equations change? Think about the circle equations you learned in the last lesson. What would the equations of translated parabolas look like if we used h and k to describe their vertices? Just as we can see the center of a circle in the circle's equation in standard form, a parabola's vertex appears in its standard form equation. Whether the parabola is vertical or horizontal, the value subtracted from x indicates the x-coordinate of the vertex, or h. And the value subtracted from y shows the y-coordinate of the vertex, or k. Using these equations in standard form, we can graph both vertically and horizontally oriented parabolas. Let's use what we've learned to graph the equation x plus 2 squared equals negative 12 times y minus 1. We'll use this chart to track the information we need. To graph parabolas, start by identifying the orientation, the vertex, and the value of p. First, let's determine the orientation. Which way does the parabola face? Since the x term is squared, this parabola will be vertical and will open either up or down. Next, find the vertex using h and k. What is the parabola's vertex? The parabola's vertex is at negative 2, 1, and we can plot that as our first point. Now, use the equation to find p and plot the focus. The coefficient of the y term is negative 12. Set negative 12 equal to 4p and solve for p. P is negative 3, so we'll measure in the negative direction, which is 3 units down from the vertex to find the focus. Our focus is at negative 2, negative 2. The directrix is the same distance in the opposite direction, so counting up 3 units from the vertex gives us a directrix at y equals 4. What comes next? Remember, 2p helps us find 2 more points. 2p is negative 6, but we can think in terms of plus or minus 2p to plot 2 more points. From the focus, we can count 6 units left, or negative 6 units, and 6 units right to plot those 2 additional points. Connect these 3 points with a smooth curve, and there it is. The parabola with the equation x plus 2 squared equals negative 12 times y minus 1 has a vertex at negative 2, 1, and a focus at negative 2, negative 2, and opens downward. Great work! To wrap up today's lesson, you'll graph the parabola y plus 2 squared equals 8 times x plus 4. The equation and the chart are in your guided notes. I'll help you get started, and then you'll finish on your own. Do you remember where to start? Correct! Start with the orientation. Since y is squared, the parabola will be horizontal. Next, let's find the vertex together. Remember, h, or the x-coordinate of the vertex, is always associated with x, even if x isn't squared. That means that h is negative 4, and k, the y-coordinate of the vertex, is always associated with y. Since we have y plus 2, k is negative 2, and our vertex is at negative 4, negative 2. As you graph this parabola on your own, remember that when you find p, if p is positive, count to the right to plot the focus. If p is negative, the focus will instead be left of the vertex in the negative direction. Finish graphing this parabola in your guided notes without using any graphing software. Okay, how did you do? By setting 8 equal to 4p, I found that p is positive 2. I counted 2 units to the right to plot my focus at negative 2, negative 2. The directrix is 2 units to the left of the vertex at x equals negative 6. Then I found 2p is 4, so I counted 4 units up and 4 units down from the focus to plot 2 additional points on the parabola at negative 2, 2, and negative 2, negative 6. Connecting these 3 points gives a horizontal parabola opening to the right. Great work! Let's take a look at our key takeaways for today. Today you learned the formal definition of parabolas as conic sections. You also learned the equations in standard form for both horizontally and vertically oriented parabolas, and then used those equations to graph the parabolas in the coordinate plane. Now that you're done with your pre-video activity and guided notes, be sure to practice graphing parabolas from standard form on your own. In the next lesson, we'll focus on converting between forms of parabolas and writing their equations. See you then! Hey, hey.